Good evening, flight test. Thank you guys for your patience with me this afternoon. I had to cancel class because I was at an event in Georgia, and it reminded me to tell you about it. But it basically involves nuclear detonation, active shooter, terrorism, and then a helicopter crash. It was intense. In any case, so what I wanted to tell you today is show you how to do the verify, and that's the last part of CIFER that I haven't mentioned, and one that I'd like you to include in your report. Because ultimately, when someone asks you for a simulation, they could either want the stability derivatives, they could want to see how well it fits in the frequency domain, or they could simply want to see how well it fits in the time domain. And frequently what you'll see in papers is it's the time domain simulation that people show, like, here's the actual flight data, look how closely our model matches. And that's what we're trying to do today. So I'll go very briefly over what we did previously, just as a quick reminder. So here, FRESPID, right, this is the frequency response identification. I won't generate it from scratch, I'll just step through this. This one is named P command, so roll rate command frequency sweep. As in, we're just doing a aileron to roll command, yeah, the aileron to rather to roll rate using the P command frequency sweeps. So if we load this case, I get these weird errors. I don't know if you guys are also getting them, but sorry if you do. Anyways, so we'll next this. I didn't put comments here, but here's the input, the ailerons to the system. The output is simply P roll rate. If we next it through there, this is one where I used a variety of different inputs. So it's labeled P command, but I've actually included the phi command as well. So CIFER, remember, lets you do multiple inputs because it takes all these time domain data sets and concatenates them together. So I did this P command frequency sweep, and if you plot this, right, you plot here's the aileron command, right, we extends high amplitude at high frequencies, and then if you plot the roll rate response, right, the amplitude starts attenuating at the higher frequencies, and that's really what we're trying to see. Trying to see that roll off. In any case, so this is from T4. This is the ones that I flew. The test 4 frequency sweep 1 using P command, test 4 P command frequency sweep number 2, and just because we have extra space, I added phi command frequency sweep number 1. These are conceivably all at the same airspeed, so we're not going to expect a variation. You can put as many of these things in. You can mix sweeps and doublets, right? Because technically these are all just inputs to the control system and outputs from the aircraft. So it doesn't really matter what you put in here as long as they all represent the same dynamic model. All right, so we next this. I previously did this, so I'm not having to do this, on the video. Clicked ailerons in units of radians. That is the input or the controls definition. On the output side, it's just P. So I've just named them the same thing. I just select P here, units of radians per second. I added that. I clicked here on all. So I want to look at the aileron to P transfer function. If you had multiple inputs and multiple outputs, there'd be a matrix of checkboxes. Auto conditioning, we're not, I just left this default. These are ones I added, 1.1, 1.52, 2.53. Those are the seconds window. I clicked on adjust and I made that change. So when I do next, I already ran this, so I won't run it here, it takes time, but save and run batch. It'll do this and gives you batch mode complete. So I clicked on C, yes, I want to exit. So once you do the frequency, the FRESPID, what it does is it calculates the frequency response from aileron to the roll rate P using the 5 different windows. And you use composite to do this averaging. You're taking this together and you're trying to get rid of noise and get better sort of a broadband coherence or broadband fit in the frequency domain without having to rely on the limitations of a single window. I will recall the last case that I did, and I just named it the same. So you can do P command frequency sweep, whatever name you want. It might give me that same error. Anyway, so we do next. And the way I had set this up before I ran this video, clicked on free, the frequency response, and when you browse, double clicked on this. This is the FRESPID result. I'm going to give me an error. Either way, the error doesn't seem to affect anything. When I clicked on inputs, it automatically pulls AILA because this is pulling from that FRESPID. This is all stuff that you guys should have already done. Anyways, outputs P, I clicked on all the windows, just as a review, as another reference. And then I clicked save and run batch, and I had that. So if I wanted to plot it, as I showed you previously, you could do qplot, but I won't go through that. Then we go to this next one. Here's this derivid, or deriv ID. Click yes. You can put any case name you want. I put lat1d, because remember, this is, you could say it's part of the frequency sweep, whatever, but ultimately we're doing a lateral direction, or a lateral single dimensional, right, roll model. So this is just looking at roll convergence. I will load this, the previous case that I did, and I'll show you all the windows just for your reference. lat1d is the name used for all these parameters. The state is P, and the output is P, right? So the C matrix is basically 1. Controls just has aileron. This is the response selection, so I want aileron to P model. And then in the next window, actually, sorry, this is the sensor coefficients. Then you have these channel assignments. I didn't do anything here. The frequency response, right? So this is asking you for, find me the frequency response that corresponds to P over aileron, right? The output over the input. And this is what I browsed. I clicked this, and under the COM here, so this is composite, P command frequency sweep, that was the name we gave it. COM is the output of the composite. A, B, C, D, E means all the windows, and from this input AL to the output P. Load that. And remember that you have to click on plot here, just to look at the valid ranges for the frequency. And this is important, because what happens is in the input data, you can, if you say go from 2 radians per second all the way up to 100 radians per second, it's going to try to fit this data, right? But that's obviously bogus because the coherence is low. So we give it a narrow window range. In this case, I did something like 2 radians per second, or 2.1, up to 23.5. It's only in this range where it's important. And remember that this input has to include the roll-off in both the magnitude and the phase. If it's just in the straight section, there really are no dynamics there for it to look for. All right, so now we go to the matrix setup. The M matrix, we'll leave it just as unity. And the F matrix, I had previously set this up, but I can redo this just for good measure. So this, to be stable, it has to be negative. We'll just do a -10. The G matrix, I'll just put it at +10. These are just default initial guess values, and it is somewhat sensitive to that. The tau matrix, put it 0, and H, just put it as 1. It is worth stressing that there's only one LP and L delta A for each airspeed. Assuming nothing changes with the aircraft, LP and L delta A are fixed for each aircraft, each airspeed rather. In the case that you non-dimensionalize it, if you computed CLP, then for the most part that should be almost invariant over airspeed. So when you're doing multiple calculations, you're running derivative multiple times to try to get these parameters, LP and L delta A. It's really important to remember that you're getting multiple answers, right, or multiple estimates for what should be a single actual answer. So the aircraft ultimately will have one, right, LP and L delta A, and you should be able to compare them. You know, if you want to compare notes with other students, you guys should have the same answers, because it's only one aircraft and we tested it at one airspeed. All right. So we go next here, next again. Could give you a warning here about the professional version. And remember that for the check marks, right, you want to make sure that the parameters are set to free. Though that's an indication to the optimization algorithm that it can vary those parameters and search for what is the correct value that matches. Update the structure, input data is okay, and I'll do, again, 1,000, start the iteration. And interestingly, it had a different result than it did last time. So normally it's a little bit better. So I'm going to go back, and this is what I get for messing with it. Under the matrix setup, it was different. Give it a little boost there. -11, 20. Oh, I think I know what it might have been. So if I did frequency response, yeah. So here was the problem that happened last time. When I reselected this, it didn't change. So it's 23.5. That's what I should have done previously. Because if you do a tracer here, and you know, I just warned you about this, and I accidentally did the error. So around 23.5 is where the coherence dips. So you can arguably select it a little bit earlier, but anyways, we'll do 23.5, and then reset everything. So as I did it previously, -10, 10 here, and we'll just next through all these windows. I think you can just click on the radio buttons on the left and be done with it. So yes, input data is okay. We'll do 1,000 iterations. I'm going to click on iterations. This is what I was looking for. So the cost function goes down to 21.3. So it's pretty good. Look at my notes here. Yeah, so sub 50 for the cost function is okay. And when you click next on here, now we start looking at these different buttons. So this gives you all the different response values, right? But I want to look at the final values of all matrix elements. If you just want to scan to see what they are, it doesn't label them. I'm surprised, but anyway, so this is LP, L delta A, and then the other, I think it's tau A we called it. Calculate the sensitivity. This is one where some of you had sent me questions. There's a Kramer-Rao, and then the insensitivity. These insensitivities are less than 10%. That's considered good. The Kramer-Rao is a little bit a little bit larger. Usually below 10% is good. But anyway, so we got -18.9 and 227 for LP and L delta A respectively, and with a 55 millisecond time delay. So those are pretty decent results. This always frustrates me. I don't know why it doesn't do it automatically, but just do number of rows, number of columns 1, in this case, since it's only a simple model. If you generate plot, this is the result. So of course I don't want to close the plots right away. You zoom in on this, and look at that. It's not bad. It's hard to say whether there's an error calculating this peak, but basically it's showing a little bit of a roll-off. It's similar. Maybe it's not nearly as aggressive as it looks like in the video. The phase response looks really good, right? So we have good results there, and this just shows you the coherence, but there's no fit. This is just from data. So we'll close this plot. That's decent data. And next, and this is really important, you have to remember to save it. And I think you can click save on the previous screens, but if you click here, on that save model structure, final matrices and responses, click save. I think it'll just overwrite it from what I previously did. This is important for the next step. And looking here to see if I have any other notes, but let me go back to this, and when we generate the plot again, it's worth stressing, this is a representation of how good the model is, but only in the frequency domain. So this is the frequency response of aileron to the roll rate, and this is a representation of the frequency domain. It's taken, how long is this? It's taken 13 minutes to get to the whole point of this video, which is how do you do this in the time domain? So again, after you've saved, you can exit with no save, right? You're sure you want to exit, but we already have that saved. It's called, what do we call it? Roll 1D or lat 1D. Now this is the verify. So you go into this next window here, which is the little squiggly line with a check mark. This is called verify. I already have one. If I browse, I already have lat1d here, but I'll rebuild the case for you guys. So I'll click on deriv ID, and I'll click browse. So this is searching which deriv ID case to load. lat1d is the one that we just set up, and we got good frequency domain agreement. Click on this one, and then when you go next, then it's a lot like you're setting up sort of a combination of FreshBid and deriv ID. So the case names, those are set up automatically. I don't know if actually these were set up automatically. I think not. But anyway, so the states are P, right? Output is P, and aileron is the control. Click next. This is for the sensor coefficients. I don't have any what is basically sensor or actuator coefficients here, so I just left all these as default. Then there's the matrix setup. This one is just as it comes. You can mess around with it here if you like, but basically this is all inherited from the deriv ID results. LP is -18. Actually, I don't know what the check is, because this one doesn't do a variation. Anyway, it doesn't matter. The HS matrix is just that. H and J, I'm not even familiar with those, but anyway, so the tau matrix here is 55 milliseconds. We'll do next. All that looks good because that's just an output of the deriv ID. Now, this is the first portion where you actually start to get into the verification. It's asking you for time history data. So you can click this first and make sure it's MATLAB, right? That's all the format that we have. When you browse, here is the big thing. When you are doing the verification, the whole point of this exercise is you do the identification with one set of data and then verify with the other. What that is like, let's say you're using the frequency sweeps to do the system identification. And now you want to see how good is my model ID. Well, you don't go ahead and select those the same sweeps. You can, but you really want to expose the model to a different set of data, one that it hasn't seen previously, because that's sort of the ultimate check. Now with brand new data, how well does the model perform? So in this case, you might recall I used P command frequency sweep 1 and 2. But let's pick a different one. So the ones that I like here are these medium, right? These are sort of reasonable doublets in the P command. So I'll click that. You can use just one. I think you only allowed one. But so P command doublet medium 1. As a reminder, we did the frequency sweeps for the IDs, and now we're saying how well does it match the doublet? And you'll see here in a second what it looks like. It wants you to put an event number. This is just 1 from flight 4. You can trim this, but just to make sure, you click on plot to make sure everything goes well, and P, this is the actual response of the aircraft. So remember, it's a roll attitude doublet, so this portion is rolling right, then maybe 30 degrees, rolling left, 30 degrees, so this is a little bit longer duration, and then rolling back to the right, back to neutral rather. Right, maybe 30, left 60, right 30. You can also plot aileron to see what aileron looked like at that time. And this is just my command, right, left, right, neutral. So this is going to take this input data, which isn't really great quality, but it's going to take this and it's going to pump it into the model, the deriv_ID model, and it's going to see what the output is. It's going to calculate the output from this and then compare measured output with simulated output. All right, start time and stop time 0. Ooh. I think if you just put both of them at 0, it takes the whole thing. We'll see. So next, it should be fine. Controls definition. So it's asking you, what are the controls? Remember, we're loading a new time history file. It knows it wants an aileron, but it doesn't necessarily know the structure. But this is the exact same thing that we did in FreshBid. Aileron, units of radians per second. They're actually percentage, but whatever. Now it's asking, what is P, right? The P, this comes out of deriv_ID. P from the model is selected here, units of radians per second. I want to determine all equation biases. This helps get the fit better. And output time history data, I want to do all of that, right? So especially P is the output that we want. For conditioning, don't bother with that. Determine biases and shifts, yes. You click on that, and this goes through the process of determining the biases and shifts. So the whole point here is it offsets whatever your results are, so that the DC component, the trim component is eliminated. All you're seeing is the variation, right? Because you just want to see the left, right, left. All right, back to here. Number of rows, we want 1. Number of columns, we want 1. So 1 here, 1 there. That's the plot layout. I don't know what that does. But when you generate the plot, this should be the final result, right? That shows how well your model matches in the time domain. Plot aileron. This is just a plot of the input, and so let's click on plot P, and this is the plot of the output. No, we don't want to do it. And here's the result. The result actually is great, right? So this dashed line is the predicted model based on the simulation, based on the system identification. If we squeeze these together so you can see on the screen, so this top plot shows aileron. This is my input. Here I am making a right, left, right, neutral, and the solid line is the aircraft response, which is measured by the roll rate gyro, right? The dashed response is what happens when you take this control input, this time history, and you pump it into the model and you run a simulation. So it's running a simulation, you're inputting into the simulation this, and you get this result, which matches closely in basically the amplitude, right? The peaks are of the same amplitude. It looks like it has lots of the same characteristics. Obviously, there are errors, but overall, from all the system identification I've seen, this is a good result. It looks like we've predicted fairly well the dynamics of the aircraft. You should be able to run this case for anything, so you can even run this for frequency sweeps, and you should see the same result. Uh, in fact, let's do that just for good measure. So I'll close this, and I'll go back to time history data. You can use any number of things. So what wasn't used is here the phi command frequency sweep 2. This wasn't part of the input data. So when you plot this, plot the p command, right? It looks a lot different. Ooh, I wonder if there's an error there. Ooh, we'll do that. Plot this. All right. Somehow it was only getting part of this. So this is it from 0 to 12 or 13 seconds. That's what it looks like. So it's not just a step, it's basically a series of steps or series of signs. So let's see how this does. So next here. Next, so all this is the same. I want to do that. Yep, and it's asking me to determine biases and shifts, yes. Close. Same plot configuration, and I want to generate the plot. Obviously that's wrong because it's only two. Hold on. Yes, I want to close all plots. So what happened here? So here's the problem. What happened last time is I only gave it a 2.5-second time increment, and because I just recycled it, it went back. So let me do max here. It should do that automatically. Let's try that. Plot aileron. Yeah, okay, so it's not going to like that. All right, so I'll stop this. And let's see if we can fix this problem. Here, 13.235. All right, I'll copy that. And when you want to plot the results, so yes, I'll do that. Close. And then, oh, so maybe auto is what I wanted to do. Yeah, maybe auto. I think I could have put like 12 point some result, whatever it is. All right, plot aileron. Great. So now this is the aileron that I was doing when I was exercising the aircraft, and I want to plot P, and this is the result. So no, I don't want to do that, and it looks fairly good. There's obviously some issues, like for instance, here, clearly there is a problem. So it's not a perfect model. In the lower frequency stuff, it's okay. It doesn't look like the phase is perfect. It doesn't look like the amplitude is perfect. So this is a harder one for it to verify. And it looks like there's part of it is this is the actual measurement of the aileron seems like it's poorly sampled. So this is where we got loss of coherence, and maybe the model didn't quite fit as accurately as it should have. We could have played with it a little bit more. This is a time domain verification on a frequency sweep. And this is the big issue. This is the reason why we do frequency sweeps, because it's a much better exercise of the aircraft and the aircraft dynamics than a simple step or even a doublet is. Let me check the notes here, see if I have anything else. I think that's it. So the last thing I'll mention is that you can export this. I'll slide this window down a little bit. If you go File, Export Setup, you can do a number of things, but you can export this to now a regular MATLAB fig. And then you can do all the usual changes. This type of plot, move this up. This type of plot presents poorly, right, in figures, because this really should be different line types. And I don't think it'll let me change the line type on this one. But if you export it, and then you do things like click on the arrow, then the line, you can right click and change the line color and line type and so on, and it makes it much more presentable in a paper than this one is. But if you desperately had to, you could probably do it with this one as well. This one doesn't have things like the I think the export fig or copy fig. So use that for sure. In your report, I would love to see your time domain verifications. You don't necessarily have to do this for everyone. You could if you'd like. Every time you run one of the models, you can show me the frequency domain result and the time domain result. You could also do this only for the one in which you have the highest confidence, the one that gave you the best frequency domain result. Then go ahead and do the time domain verification there. I believe someone else asked me something else regarding the number. Somewhere here, if you click next, you can, this is as an aside, you can click this and store it for later. But there also should be a measure of how good the fit was. I don't know where that is. If I do see it, if I do remember it, I will let you know. But in any case, that's the verify. Please insert that into your report. Look at the feedback that I gave you. I typed up a couple of points of feedback for everyone. Those are the same things that I'll be stressing, right? The presentation, how you're doing the data analysis, how you're summarizing the procedure, and certainly the quality of your results and discussion. All right? I will send another update here shortly on the flight test. Take care, guys.